Good morning, sir.
Good morning, guys. Okay, let me enable the attendance first. Attendance. Uh, okay, attendance enabled. You can start giving your attendance. One more thing. Have you guys already accessed the Google Drive folder of the course? Good morning, everyone. Yeah, because have you guys accessed it? I mean, anyone? I am putting my slides there.
Yes, sir, I have.
Yes, sir.
So it
Yes.
is accessible, right? I mean, I don't
Yes,
understand
sir.
some.
It's accessible.
Yeah, so I'm not sure because I have not actually shared it individually. I have shared it with your whole batch. So maybe those people who have not been able to access it, they are probably trying to access it from their personal. That's why the issue is. And this annoying beep thing is back, even though I have made the changes in my WebEx account. This thing is still there. This is why I just hate WebEx. I just hope. Yeah. Please. I have sent another form yesterday. I will say I'll keep sending these no question forms. All you have to do is simply submit them, and then you get your attendance. I do wish there is another better way. I know. I'll see. I actually did not have so much time this week. I'm already overloaded. I have to prepare the question paper for B.Tech third semester. There is an exam in the same slot as the classes tomorrow, 10 to 1. So that is why I can't take class tomorrow. I'm going to cover tomorrow's lecture today itself. So, there are so many things that are there on my plate. I'm just trying to somehow cope up with them. Okay, I have 76 responses till now. 76 attendance. 77 now. Good morning, everyone who is joining now. Please just submit your attendance first. That let us get that away from us so that we can start. 82 till now. Uh, 90. So please make sure that you mark your attendance before we start. Let's get this annoying thing away. I really don't like taking attendance. Let me be very frank. If you come to class for attendance, you don't study. So I only want people who want to study to come to the class.
Excuse me, sir.
Go ahead.
Sir, I am Millie. Sir, how to mark the attendance?
Millie, you would have received an email around 11:30 or so yesterday night. there will be a Google form that I shared with you. Okay, you just have to submit that form. That's it.
Okay, sir.
Open
Thank you.
the incognito tab in Chrome.
Yeah, Tia is the expert. She faced this issue yesterday.
No, sir. Yashwardhan told me how to submit the attendance.
Okay, okay. So essentially, the problem is if you are logged in from some other Google account, you won't be able to submit that form. So you have to. Yashwardhan is saying no, he didn't tell you this. Yeah, if you are logged in from some other account, then that form won't go through. So this is simultaneously the best thing as well as the worst thing about Google. You can be logged in with multiple accounts at the same time, but sometimes you don't understand which account you are using to access a resource. So yeah, there is something interesting going on in the chat. So anyhow, so basically, okay, let me check how many have already done it. 123. I guess there won't be any more than 123, right? Why would there be more than 123? And 124. What is the batch size? Oh boy, did I stop? Okay, okay, I probably made a mistake. I should have checked. Okay, that I will do anyhow. So I probably have to restrict to one response. Yeah, I have done it now. Anyhow, that is my mistake. I'll just remove the duplicates later. Uh, so we have a lot to cover today. So let us start straight away. What I'll do is I'll start my video because some of you may have limited bandwidth. I'll just share my screen. And before that, okay, let me just share the screen first. Mhm. Just share. Okay. So before that, have you guys actually checked out this particular uh, drive folder? I have shared it with everyone. Um, I received some emails saying that they are not able to access this folder, but uh, I can actually tell you that I have not really done anything like this. I mean, if you check the share settings, they are basically shared with the batch. I have not shared it with individual people anyhow. So I'm not sure why some of you will be able to do it and some of you may not. Uh, Anyhow, just I assume it is the same problem, right? That Google account problem. So if you are not able to access this is a Google account problem. Check the Google account you are using, and I feel it should be fine. So someone said something about classroom. What is it? How do I get this thing done? Okay, right. I'm not sure how to look at these chats in this mode. It is not allowing me to go back to. So from here onwards, if you have like anything important, I do try to look at the chats. But if I cannot look at your chat, please unmute and ask. Okay. So by the way, before we start, a revision of yesterday. So what we know already, there is a CPU in a computer. There are some input devices. There are some output devices, and there is a memory element. Okay, this memory element we also call it as main memory. In fact, this is what we are going to. Yeah, cache memory is something that is within the CPU. But yeah, as I said, let's not go in the direction of cache. Cache itself is a different topic altogether. Uh, Unfortunately, I just that what does that mean? इधर उधर निकल जाता हूँ that video. So I keep on distracting myself. I keep on teaching you stuff that is really not my job. My job is to teach you programming. And I start teaching you operating systems and computer organization and switching theory and all those things. So anyhow, I'm uh, I'm leaving that task to your computer organization teacher. Okay? So we'll talk. They will talk about cache. हाँ वही माफ करना गुस्से में इधर उधर निकल जाता हूँ. So I keep on distracting myself. Sorry. So I'm not going to get distracted in that direction. Cache is something that your computer organization teacher will teach you. If you know everything in advance, you are going to make his or her life hell. So, I'm not going to be responsible for all the abuses that he picks up. So leave something in the suspense. You'll read about cache later. So anyhow, basically the issue that we saw yesterday is that everything in the hardware is basically a 0 or a 1. It is just two states of that transistor. And basically interacting with this hardware at that 0 and 1 level is very it's tedious, right? Because we really don't speak 0 and 1. We speak in natural languages. So what people came up with was they came up with the solution called operating system. So operating system is basically an assistant. It's your assistant which talks to the hardware on your behalf, right? And it basically operates the hardware on your behalf, and that is why it is called as the operating system. And hardware is just a glorified term for electronics that is there, right? And all the electronics that we looked at yesterday, people also call it hardware. So the operating system basically is a kind of a kind of virtual layer. Just imagine it in your head. Uh, that this layer is the layer that actually talks to your hardware, and it manages your hardware. One of that thing. So I received a lot of emails yesterday. They were not really sure about what do people mean by repeated computations. Why do we really need a memory? So today you will understand this, right? Why do I need a main memory? We will walk through a very simple example, and with the help of it, you will understand why I need that. So main memory element, even though it is not technically accurate, the colloquial term that we use for it is RAM, right? So you might have used this term so many times. RAM. You would have said, my laptop has these many GB of RAM. That same RAM. For now, just assume that RAM is basically your main memory, the memory that I have shown in that diagram. And main memory is basically where your operating system puts some instructions, and your CPU, it just picks up those instructions from the main memory. So remember, I told you that the speed at which the CPU operates is much higher. It's in sub-second level. Whereas if I start giving inputs to the CPU 0, 1, 0, 1, even the best typist in the world will only have only he'll be slower or she'll be slower by many magnitudes. So what really happens is the operating system puts some instructions, whatever computations you want to do. These instructions operating system puts inside the main memory, and then the CPU just picks up those instructions from there and executes them. Now, if you whatever data is required to execute those instructions. So for example, the instruction is addition, then you need to give me two numbers to add, right? So that is the data part. So the data that is required to execute the instructions are also kept in the same main memory. And this is basically an example of what a main memory looks like. By the way, in the previous lecture, I realized that I have only made 15 boxes here. But it just assume that these are 16 boxes for now. I will, whenever I will get time, I'll just add one more box at the bottom. But just assume like there are 16 boxes here, one below the other, and these are places where I can store some bits, as in one bit basically means I can store 10 or a 11. So 0 or 1, I can store a 0 or a 1. And the capacity of this main memory is 16 bytes. So if you remember the discussion we had yesterday. So a byte is basically a collection of 8 bits. So what I'm telling you is each of this box is basically 8 smaller boxes in which I can store a 0 or a 1, a 0 or a 1. So basically this one box is essentially 8 smaller boxes. So this is one byte. Okay, and what I have here is something like this. These are binary numbers. Okay, and their corresponding decimal numbers. I also shared a resource with you guys to revise or study about number systems yesterday, right? So if you have studied that resource, you would now know that if you convert 04 into binary, it comes out to be 0110 0100. Is my voice breaking?
Hello, sir.
Yeah.
Sir, keep your mic a bit far from you, sir. We are getting a lot of noise disturbance, sir.
Okay, fine. Actually, no, there are some disturbances at my home as well.
So
Anyhow,
now it's okay, sir. Now.
okay, fine. Good, good. So I actually was keeping it closer to my mouth because I thought there is a lot of background noise. Uh, so so I thought maybe I should keep it closer. But yeah, fine. Good, good, good. You can understand. That is the whole point. So, so it is something like this. I have this memory, and you can see that there are some numbers written here. So, what these numbers are, they are basically addresses in the memory. Okay, and addresses as in if I want to store some data at a particular in one particular box, I basically say store some stuff at 01111 0111, right? And then it means that this data is going to be stored in this box. Similarly, if I say store something at 1100, the data will be stored here. So essentially, this memory, it has addresses. Okay, so every box has an address, and every box has 8 smaller boxes, and each box can store 10 or 11. And the so the width of this memory is 8 boxes. It is 1 byte. We call this as the word length of my memory. My memory has a word length of 1 byte. It is possible to have it even wider. So it is possible that at each address I store more than 1 byte. I could keep more than 1 byte as well. But let us again, I'm probably infiltrating in the computer organization territory again. So let us come back. Okay, so basically for now, just assume that this is basically a word. We call it a word. Okay? A word in the main memory, and it consists of 1 byte, not 1 bit, but 1 byte. So there are 8 bits. So whenever I want to read or write from this main memory, I do that in I don't read a single bit. I basically read 8 bits at a time, or I store 8 bits at a time in this memory. So yeah, for now, just assume it is the word length is 1 byte. We can store both instructions as well as data in this main memory. Okay, this is just an example that this is how my main memory looks like. Some part of this memory has instructions. So what does this instruction says? Load data at 0110 in AC. I'll tell you what AC is. Similarly, there is another instruction: load data at 1011 in R1. Then there is another instruction: add R1 to AC and store result at 1111. So this is basically the instructions part that I said, that operating system is going to put some instructions in the main memory, and at the same time, whatever operands are required for these instructions to be executed, like let us say I want to add 8 and 13, I store 8 and 13 somewhere in this main memory. Somewhere, it is not necessarily here, it could be anywhere in any of these boxes, but I must know where they are. The address of the box, I need to know where they are. So now let us just revisit the CPU that we saw yesterday, and today we are going to see what a sample program looks like. Right? So this is a programming course. This is going to be your first program. So remember that there is a control unit, and this control unit is is basically the boss of the ALU. It decides when to use ALU and when not to use ALU, and what part of the ALU is to be used. So let us take an example of addition. So we want the control unit to add two numbers, 8 and 13. And now we have to somehow put these instructions, the instructions that you have to add these two numbers, as well as the numbers themselves within the main memory. And this is how it looks like. You have these instructions and the main memory, and there is something more here, right? So remember the registers that we were talking about yesterday. Here are some examples. So there are three registers that I'm showing here. The first register is called PC, the second is called AC, the third one is called R1. There's something that you have to understand here. The size of these registers, the width of these registers is exactly the same as the width of my main memory. So if my main memory, if this box can contain 8 bits, this box can also contain 8 bits. So there has to be a matching. If my main memory's width is 2 bytes, my registers are also 2 bytes. If my main memory is just 1 byte, my registers are also 1 byte. This is the only thing that you have to know. And there are two special registers here, PC and AC. And then there could be one or more general purpose registers in my CPU. I just name them like R1, R2, R3, and so on and so forth. So what does this AC stands for? So AC stands for the accumulator register. Okay, what accumulator is basically, uh, you know that ALU is going to perform some operations. Okay, so what are the operations that ALU could do? It could probably do some arithmetic operations like adding two numbers, or it can do those logical operations, and or not. So if the operation it is doing is a single operand operation, so if you remember, not is an operation that requires only a single Boolean variable. So what happens is, if the ALU has to perform an operation for which only a single operand is required, I use this register called AC for it. Now you would understand that AC has a size of 8, right? 8 bits can be there. So essentially what happens is ALU performs this NOT operation simultaneously on 8 different bits. So if the NOT operation is, so basically the NOT operation simply flips your bits. If the input is 0, the NOT operation, the NOT function returns 1. If the variable is 0, the NOT function returns 1. If the variable is 1, the NOT function returns a 0. And now assume that there are 8 instances of this main memory. Okay. So okay, so this is my main memory. So what exactly happens is, main memory is essentially, there are boxes here, right? So each box is capable of storing some data. Okay, and what exactly is the data? It is this 0101. Don't worry about this. Essentially, I have just written them like this in order to make you understand. This too is stored in something in a similar fashion. There are basically a sequence of bits here, 1110, something like that. Okay, but I've just written it like this so that for now, just bear with me for now. No, I'll tell you what exactly does this mean. But basically what I'm saying is, there is a space in my computer where I can go and write something, where I can actually keep some zeros and ones, and this space I'm calling as the main memory. This main memory has addresses. Okay, so basically, assume that they are more like, if you go on a joy ride. Okay, those rides in which they have these seats, right, one behind the other. So let us assume that a main memory is one of those rides. The first seat is address 0, the second seat is address 1, the third seat is address 2, so on and so forth. And if there are total of 16 boxes, actually there are only 15 that I made here. I miscounted, but there are essentially 16 boxes here. um, and uh, and basically each box has an address. So this is box number 0, this is box number 4, 3, something like this. So and their corresponding binary representation is written here. So 05 is represented as 0101 in binary. 9 is represented as 1001 in binary. So this is just an organization of how I can store data. I have a place in my computer where I can store bits. Okay, I can store by 16. Again, these questions you'll keep coming up with once in a while. We are going to operate in uh, in multiples of 2. So it's similar to say, why do you have 100 and 1,000 and 10,000? Okay, whenever we talk about money, we usually talk about hundreds and thousands and 10,000s. Why not 99? Why not 98? Right? It's no audio. Okay. My audio is breaking, guys.
Yes, sir, you are
So it's
audible.
fine.
Yes,
No,
sir.
sir.
Okay.
Sir, I think it's fine from your side.
Okay, fine. So basically that question, right? I think the best way to answer it is when we talk about money, we usually talk about things in the multiples of tens and hundreds and thousands, right? We don't talk about them in multiples of 51 or 77. It's just easier. The mathematics is easier uh, when we do it in terms of not multiples. This was pointed out to me, powers of 10. Um, the similar thing, we are now in the binary world. In the binary world, the base is 2. So many a times when I'll have to give examples, they'll be in powers of 2, not multiples. I'm sorry. I somehow have this habit of using the word multiple instead of power. I don't know why it happens, but please forgive me for that. The idea is not multiple, but power. So it has to be in powers of 2. Um, exactly why
Sir,
it happens? Yeah, go ahead.
sir, are those written in the starting 00 trip, matlab, 4 zeros and 3 zeros and 1 3 0 and 1 00100011? Are those addresses of the
Yes, yes, yes,
bytes?
yes, yes, yes. Okay, so basically, it's just like giving them numbers. As I said, if you stand in a queue, the first person is given a number 1, the second is given the number 2, the third one is 3, 4. It's just that in computer science we start counting from 0 instead of 1. Okay, so if there are
Sir,
why
why you mentioned 8 on address 6? Sir,
just
000 100.
uh, please repeat. There was a question on the chat as well. What did you ask, Nitish?
Sir, why you mentioned 8 on address 06? Sir, ye 0001000.
This and this.
Yes,
Okay,
sir.
okay, the data that is stored at memory location 6 is 8. So
Yes, sir.
right? So this is representation of 8 in binary.
Okay, sir.
Okay, so 8 in binary. So you understand this is the address. Okay, so that is like saying, as I said, if you are going on a joyride, they have those cars, right? One behind. Please unmute yourself, okay, and ask me questions after I have done. So basically, if you go in a joyride, there are like these cars, right, one behind the other. So one way to look at those cars is you say this is the first car, this is the second car, this is the third car, and then you say in the third car, who is on top? In Aditya Gupta is in the third cart. Okay, so 8 is Aditya Gupta and 6 is basically the third cart. Okay, is it clear now?
No, sir, it's not clear.
So basically, this is the data. These zeros and ones is the actual data that I am storing in the memory. Okay, and where am I storing it in the memory? I have divided my memory into 16 different slots. Each of these slots can be used independently. So what is stored in this slot has nothing to do with what is stored in this slot. Okay, so I can actually go and read or write something in this memory at one particular location. Okay, so as I said, assume that you are inside a bus. Okay, inside a bus you have these seats, right? And Abhishek, can you just mute yourself? Okay, so in a bus, when you enter a bus, these buses have these seat numbers, right? So what you're seeing here and here, these are seat numbers, and this is an actual person on that particular seat. Okay, the name of the person is 8. Does it make sense now? So these are the seat numbers, and this is the person sitting on that seat.
Okay, sir.
You got it?
Sir, the data 8 is also mentioned on 9. Can I repeat that?
The data 8 is?
Sir, the data 8 is we put on address 9.
This is address 6 actually.
No, sir, the same data we put on address 9.
Yeah, that is fine. These are all independent. You can put the same data on all these locations. It doesn't matter.
Okay, sir.
Yeah, they are independent of each other. They are, as I said, right? It doesn't matter if it is possible that you put the same person on 2 seats of the bus. I mean, of course, you have to clone that person, but if you can clone a human being, you can put the same person on all seats of the bus. That is the same idea. Okay, but
Yes,
they are
sir.
yeah, they are independent of each other. I had some questions on chat that I could not read. If you have the query, then please ask.
Sir,
Yeah.
sir, I'm asking that memory at a particular location in means this 16 bytes means in 1 byte there is 8 bits. Sorry, sir, and they are particularly 16 location in main memory.
Yes.
Hello, that only you are trying
Yeah,
to
yeah.
explain. No?
Yeah. Your main memory is a 16-seater bus. So there are 16 seats, and at any particular seat, any particular human being, that is a number, can go and sit.
Okay, got it, sir.
Any other queries? Yeah, any other queries?
Sir, you did mention that you have only written 15 bytes, but
Mhm.
including the first 00 byte, aren't there a total of 16 bytes?
Including the first 00 byte, what is it?
Aren't there a total of 16 bytes?
There are total of 16 bytes. Sorry, I'm not able to understand your question.
Till 00, 01, 02, there are a total of 16 bytes. So do we have to include the last 16th byte that you have missed in the table?
That is just like for representation, that there are 16 boxes in this memory. So basically, I am telling you that this is a 16-seater bus, but the 16th seat is currently not visible. That is the only thing. I mean, it is just
No,
for
sir,
representation.
sir, including the first box, there are 16 in this table only.
Let me count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, I have to count again. I'm 1, 2, 3, 4.
No, sir, it's 15 only.
So you have made
It's
made 16 values, but you have didn't make the box.
Yes,
Yeah,
there are 15 box only, sir.
yeah. So I forgot to add the last box. The space was over. So it's my fault. I'm really sorry.
Okay, sir, I got it.
It's
Right.
really
So
fine, sir.
each box has an address. Just assume like this. Okay, and the addresses start from 0 and go up to 15. Right. Okay. So is the concept of a main memory clear now? What exactly is main memory? It is just like a bus,
Yes,
and and in each seat there can be a value. That value is a number, or it could be an instruction. That is it. That is the only thing that I'm telling you. The instructions themselves are also stored as numbers, by the way. I will tell you how they are stored, but for now just assume that I can either store an instruction or some data. So is it clear now? Let's show you some magic. So this is exactly how your computer works. So in the beginning, by the way, I was telling you about these two registers, right? Okay, so now there are two special registers. One is accumulator or AC, and what AC is used for is something like this. Your ALU, it is capable of performing some operations, right? It can, as I said, it is a very dumb unit. It is just some current flowing through some electronic components, but it is capable of performing those operations. It cannot store anything, right? So basically, you pass current from one end and the current exits from the other end. Nothing is stored anywhere. So if you want to keep your data safe, right, even after the addition, so it's uh, if you know, it's like water. If you pass water from one end of the pipe, it will flow out of the other end of the pipe. It won't hold, right? The pipes are not capable of holding the water. Uh, yeah, Kirchhoff's laws. I mean, basically, we are not really at Kirchhoff's law. Kirchhoff's laws are used for networks, basically, where your current gets distributed. I'm just saying that current never. So you can't store electrons like this, right? I mean, basically, they keep on flowing. You can store charges, right? But that is a different thing altogether. What I'm saying is that ALU is a static thing. Okay, you pass stuff from one end and it just exits from the other. If you want to hold on to some information, okay, so it's like saying I have only pipes, then I cannot hold water, right? I need these tanks, so I can make the water go from one tank to another tank, but I can't hold them in pipes. So ALU in some ways is just a combination, a complex combination of pipes. It cannot hold the water. You need these tanks. Yeah, capacitor can store charge. Thank you, Yash. So basically you need some tanks, you need some places where from where the water flows and to where the water goes. So these tanks are your registers. So a accumulator is a register which is used by ALU to perform some operations. So ALU stores the results of the operations inside the accumulator register. So that is the use of accumulator. Once the let us say and the and operation or the not operation or the addition, once it completes, it goes inside the AC register. Okay, so that's this. And as I said, registers are basically memory units. They can hold on to the value that you give them until they are powered. So basically at the end of an operation, AC stores the final result of that operation from the ALU. Okay, and let us say if I need two operands to perform this operation. So let us say I'm trying to make okay, so let's say I want to make some color. So I have two different colors. Okay, I have water of two different colors, and now I have to make a third color. So basically, I store the water of one color in one tank. I store the water of another color in another tank, and then there are two pipes. These pipes somehow intermingle with each other, and then there is an output. Okay, I store that output in some third tank, right? So basically, sometimes the water doesn't flow from a single tank to another single tank. You can mix multiple tanks water together, and this is basically what it says, that ALU may have to perform an operation which requires two operands. So, for example, for addition, I need two operands. I can't add just eight. I need 8 and 13. So, in case I need two operands, I can use these multi-purpose registers called R1, R2, so on and so forth. But again, the final result of my operation, that gets stored in the accumulator register. And PC stands for program counter. So I'll tell you what program counter is, as you will come to know. Essentially, the control unit uses this particular register to store an address. So this is the difference. Accumulator stores data, after some operation, whatever is the final result, that is a data, right? I mean, 8 plus 13 is 21, so I have to store 21 somewhere. So that 21 is stored in ALU, in AC. This program counter register it stores addresses, so that 0110, 0111, 1111. So those four bit addresses, right? Program counter is a register that stores some addresses. It doesn't store value, it doesn't store data, it stores addresses of memory locations within the main memory. And this address, the address that program counter actually contains, is basically the address of the next instruction that the control unit is going to execute. So let's walk through an example. So this is what happens, somehow let us assume that this instructions and this data has been stored in the main memory. How does it happen? I don't care. Let us assume that I have this instruction and data in the main memory somehow. Now let us assume that the control unit wants to execute this particular set of instructions. By the way, you can't hear me. Is it audible, guys?
Yes, sir.
Yes, sir. Okay.
Yes, sir.
Yes, sir.
Okay. So sorry. I'm really sorry. I mean, we will share the recordings with you. So once in a while, if you don't get it, I'm sorry. Uh, Anyway, so basically this is a small program here. Okay, so a program is nothing else but a collection of some instructions. Okay, so I have four instructions here, and this I'm calling this as a program. A program is basically a unit of some kind of computation not in terms of the computer, but for us, right? So a program it performs a task for me. So for example, I will write a program that can add two numbers. Okay? Now, in order to actually do that at the computer level, I might need multiple instructions. Okay? So these are the instructions that I'm going to use in order to add two numbers using my computer. So the first thing that happens is something like this. My control unit, it somehow knows, again, I'm not going to go into detail of how, but the control unit knows the starting address of the program in the main memory, the starting address, the first the address of the first instruction. So in this case, the first instruction is stored at memory location 0000. It is not necessary that it is here, it could be anywhere in this whole memory. It's just that these four instructions are contiguous as in, uh, if if the first instruction is at memory location n, the second is at memory location n plus 1, the third instruction is at memory location n plus 2, and the fourth instruction is at memory location n plus 3. It could be anywhere in this memory, but all these four instructions are one after the other. That is the only requirement. Okay, and if that requirement is met, what really happens is, in the first step, just as soon as you start executing this program on your computer, the first step that happens is the memory location, the memory address of the first instruction of your program is loaded into the program counter. This is done by your control unit. Ankit, do you have a question? Okay. Sorry. So basically, yeah, Ankit, do you have a query? Okay. Then it could be fine if you just mute yourself. Thank you. So the idea is, when the program starts executing, the first step that the control unit does, it loads the starting address of the program in the program counter. So you can understand that this PC, once again. So PC, as I said, it is a register, but this register is different from the other registers. Other registers are used to store data. PC is a register that is used to store addresses within the main memory, right? So the possible values for PC is 0000, 0001, 0010 up to 1111. So I can only have these 16 possible values in PC. AC can have any 8-digit, 8-bit data. R1 can have any 8-bit data, but PC can only have these 16 possible values, because PC is a register where I store an address. And what is so sacred about this address? The control unit will execute the instruction. The control unit will basically go to this particular location in the memory, and whatever it reads from there, it will assume that it is an instruction and not data. Okay, so whatever is in PC, sir, these instructions are stored in main memory. Yeah, Shivam, these are all stored. Everything is stored in the main memory, the data as well as the instructions. Actually, I'll show you that these instructions are also not LOAD. They are also basically 0110 something like this. But I'll
So,
tell
me,
you.
so, so my main question is that when we turn on the computer, then these instructions are stored in memory, or when we execute
Yeah.
the operation.
Okay, so again, this is something in the field of operating system. For now, just assume that your operating system somehow knows how to store these instructions in the main memory. Okay,
Okay,
it
sir.
is the job of your operating system to store this in the main memory. Exactly how that happens, that is something that you will study in operating system. But
Okay,
but
sir.
but your operating system will store these instructions as well as these data items in the main memory. Okay, and then the program starts executing. The first thing that control unit does, it points. Actually, it is not control unit, it is the operating system again, but for now just assume that the control unit puts the starting address of the first instruction in the program inside the program counter. So this is the first step towards executing a program. Now what happens? Control unit goes and reads whatever is written at this particular address. So actually these 4 bits are just a waste. I'm only going to use these 4 because this is a 16-byte memory. The addresses go from 0000 to 1111. So essentially these 4 bytes are a waste. But what it means is this program counter can be used for even larger memories where my addresses can be in 8 bits, right? This is just the idea. But for now, just assume that my control unit will basically go to location 0000 inside the main memory, and there it says it sees that there is an instruction. The instruction says load the data stored at location 0110 into the AC register. So this is an instruction, okay? And control unit somehow executes this instruction. So basically what happens is there are some wires from main memory to your CPU, right? Those buses. So with the help of those buses, whatever is stored at location 0110 is copied as it is into the accumulator. So 00000100 that gets copied here 0000 Is it clear? So this is how the first instruction of my program got executed. It is a transfer instruction. So I just use my buses to copy some bits from here to my register AC. Now what happens is this program counter is there is a hardware within your CPU which will keep on incrementing this program counter by 1. So if currently the value in program counter is 4, after I execute one instruction, yes, Harsh, what is the question? Harsh, you raised hand, right? It was just a mistake, is it? Yeah, fine. I also do this. Okay, so what happens is if the previous value of program counter was 4, after executing one instruction, it will automatically become 5. 5 as in if it was 0110, it will now become 0101. And after executing one more instruction, it will go to 6. So it will become 0110. So program counter automatically gets incremented by 1 after each instruction is executed. This is automatically done. So now the previous value of program counter was 0000. It has now become 0001. Okay, so now not audible.
Sir,
Yeah, go ahead, Rishi.
sir, basically this means that operations are loaded in starting bytes, and the inputs which are used for particular operations can be stored in any of the given bytes or addresses?
No, that is not. And in fact, these operations can be stored anywhere. What you really need to know is what is the starting address of the program. Okay,
Okay.
this
Starting
data
can
could be, so it
anywhere
is
and
possible.
the
Yeah, anywhere, anywhere.
decimal wise.
Sir, if we'll give the instructions and they'll continue to be in 0406, then what will happen to the data stored in 06, where it will go?
It's there only. I just copy this from here to here. Nothing happens to this.
Then we are also uh, giving instruction in that address and also the data. Can this happen at the same time?
Sorry, I didn't get what is it?
I mean, there is a data in 06 address, the 8 which we have stored, and also we'll give the instruction which PC will get. So the data and instruction they are together in the 06 address at the same time.
Not so. 06 address only has data. 00 address has an operation code and an address and the name of a register. No, you don't have to make any notes, Panchdeep. I will give you the lecture recording. I will give you these slides. If in future I will also give you runnable programs in C that you can simply download and run. Okay, so just listen to the lecture. So basically, we essentially have data at this location 6, and I have an instruction at location 0. Okay, now this instruction has 3 parts. It says the operation is load. The address from which the loading has to be done is 0110, and it has to be copied into the accumulator register. So there are 3 pieces of information on address 0, and on address 6 there is a data item which is basically 8. Is it clear, Tia?
Yes, sir.
Okay, yeah, please, I mean, if I miss any queries on the chat, I try my best to read them, but if I cannot, yeah, go ahead.
Sir, what if the instructions are not continuous? Like if there is a break, does the program stops there or it just ignores it and moves on to the next?
There is never a break. This is a
Okay.
requirement. The program has to be stored continuously. Okay, so there is never a break. Don't assume there will ever be a break. There can be some other things known as branching, but it is an advanced concept. We are not discussing branching today.
So basically, the program counter has the address of the, let's just say, the seat in the main memory from where the operation has to be executed. But where is the program counter getting it from?
At the beginning, it is set by the operating system. Okay,
Right.
and then from there onwards, it just keeps on
Increments.
going to the it just increments for the next address.
Thank you, sir.
Okay. Yeah, instruction is also a data. This is a very good question. I will just cover this, Mridul. Let us go through this. I will tell you what instructions are, and how they are stored. So, so for now, what happens really is that now PC has gone to 001. So the next instruction is, it says load data at from location 1011 in the R1 register. So what happens is now these bits are copied into the R1 register, and again the program counter now has incremented by 1, so it is now at 2, whose binary representation is 0010. Okay. Yes, Sanskriti, you have a question? Okay, yeah, so maybe I think you just raised hand. If it is 6, what was some question? If it is 16, I could not read. Guys, like, it's difficult for me to read chat. If you have a query, just unmute and ask.
So can you repeat about R1 once again, sir?
Yeah, so it's the same thing, right? I mean, now this particular instruction was executed. This instruction is done. It has been executed. Now my program counter has value 0001. So this means my control unit is going to read whatever is stored at this particular location. It reads it. It's what does it say? It says uh, transfer the data at memory location 1011 to the R1 register. I also have some more registers within CPU. They are known as R1, R2, so on and so forth. They are used as and as often required. So what happens is once this in AC. So AC is, so as of now, there is nothing special about AC. Just consider AC is another R. Okay, it is R0. There's nothing special about AC as of now. AC is just another register in the CPU where I'm going to transfer some bits from the main memory. Okay, there's nothing special about AC. What is special about AC? I'll just tell you in a second. So you have some registers within the CPU. What these instructions are saying is pick up some value from the main memory and copy them in these registers. Other than PC is not used for copying anything. PC is just, it's like, it's out of reach for these instructions. PC is managed by the control unit because it is used to store addresses. But all the other registers, you can use some operation. You can call it load operation to bring data from the memory and store it in these registers. Is it clear now? What is AC? AC is nothing special. It is just a place to store some data. Is it clear, guys? Okay. So now I have two load instructions. So these load instructions are basically going to load these two data items. Not as PC. It can be used as AC. It's not usually used as AC. PC is a different thing altogether. But for practical purposes, R1 and AC are interchangeable. We are loading the number to be operated because at some, as I said, right, these registers are the water tanks where my water resides before I ask them to flow through the pipes. The pipes are your ALU. Okay, so you have to hold the water somewhere. As I said, right, let us say you have to mix two different types of water. So the first operation fills water in the first tank, the second operation fills water in the second tank, and now in the original AC after execute. I did not read that chat just now. Original AC, something like that. You can ask, unmute and ask. Instead of R1.
Well, just like in first command, we have loaded the data in AC.
Yes. You can interchange. So you can first load R1 could be here and AC could be here. No issues.
But AC can be used only while
No, it's not like that. So basically, I need two tanks, right? It doesn't matter which tank I fill first. I could fill this tank first or that tank first. It's like this, right? The task I want to do is I want to mix the water from these two tanks through my pipes. It doesn't matter if I put red water in the left tank or red water in the right tank or yellow water in the left tank. Yeah, go ahead.
For the second command, why we are using R1 as an intermediate to reach to AC? Why are we not directly reaching?
So basically, your ALU, as I said, right? It is a set of pipes, and there is one end of this pipe, and where is that end lying? Within your CPU. It is not lying in the memory. Okay, so from memory you have to bring the water first to your CPU. And where do you bring it first? So basically, you are asking a tanker to get the water from Ganga or Yamuna, and the tanker brings up the water. Okay, and then you keep the water in the tank, and these tanks are your registers. And now, once you have all the different types of water in the tanks, you switch on the pipes, and now the water is going to flow and get mixed. Is it? Can you understand? Right. So now the right. So basically these AC R1 are two tanks. It doesn't matter which one I fill first. It is I can fill this one here or this one there. That doesn't matter, right? Addition is commutative, so it doesn't matter. So basically, then the next thing that I do is in this particular instruction, I say add R1 to AC. So this is the time when my ALU is called upon. It says that so the control unit says you have two numbers. One is stored in AC, another one is stored in R1. Now just add these two together. And there is a reason I write add R1 to AC instead of writing add AC to R1. So this is where AC is different from the R1. So basically, the ALU is built in such a way that the result of an operation is going to get stored in AC only. Okay, the result will not go to R1. So when I add R1 plus AC, basically what happens is the content of AC will be overwritten. So whatever was the previous content of AC, that will be overwritten by a new content. So now, after this particular execution, AC now has the value which is basically the sum of R1 and the previous value of AC. So it's like this. I had those two tanks, right? And one of this tank was AC, the other one was R1. I joined the pipes together, and now the output pipe, I have put it back into the AC tank itself. Does it make sense? So now the water will come from both the tanks. It will get mixed, and then it will go back to AC. Does it make sense? Is it clear? Do I need to explain this again?
Yes,
Yes,
not much.
Avian.
Yes, sir, it's clear.
Yeah. So basically, this is the idea. This is where AC is different from R1 or R2 or R3. The output of my ALU is going to go always inside the AC. Whatever operation I do, it will always be stored inside AC. The content of AC will be overwritten. Whatever was there, that is lost. Now I have a new content in AC. Okay. And again, the program counter has again gone ahead by 1. So it is now pointing at this particular location. It says store result at memory location 1111. So again, please pardon me, there should have been one box here, and that would have been the address 1111. But for now, just assume that this is my last box, the 1111 box. So essentially what happens is at the when this store operation gets executed, I copy the content of AC to this particular memory location. Okay, and now these XXXs essentially means I don't care now. No, my program has been executed. I don't care now what is the value of these bits. It could be 0 or 1. I don't care. X stands for don't care. Go ahead.
Sir, what if the output is more than the storage of AC? Will it store
Okay.
there also?
Okay, so this is a problem called overflow. As of now, just assume that your computer cannot add numbers beyond a certain limit. Just assume as of now, right? So the operands, if the final result is beyond 8 bits, for example, then something weird will happen. We call it overflow. When you will program in C, you will see that very often. So, but for now, just assume that your operands are within the reasonable limits. So you do not have a, so even after addition, you can see that the operands were 4 bits. The final result is 5 bits, but I can afford up to 8 bits, right? So everything is fine. But let us say if the operands themselves were 8 bits, the result would have been 9 bits, and then I cannot store the 9th bit here. So I'll call that operation as an overflow. It is a problem. But for now, just assume that everything is within the flow.
Okay, sir.
Okay.
So how
Yeah, go
does
ahead.
the CU know that the program has been terminated?
Very good. So this is actually a very simple example. Usually you have markers. So there is a start marker and there is an end marker. When you will do assembly language programming, you will read about it. So there is a way for control unit to understand that the program has ended. Okay.
If the program counter is in the 16th box,
yeah,
then if the program counter is in the 16th box, then the next counter goes to 1.
the next
0.
Yeah, it goes back to 0. This is the whole concept of overflow. But as I said, then this is usually it never happens. There are ways to control it. Okay, so yeah, some chat came up. I didn't see.
Sir,
Go ahead.
can I ask you?
Yeah, go ahead.
Sir, like that, there in 002, there is add R1 to AC. If I write that add AC to R1, then in that case, is that way possible that overwritten in R1 will be
No, it is not allowed. So that is an illegal instruction. The legal instruction is add R1 to AC. Add AC to R1 is not allowed. Let us just leave it at that.
Okay, sir.
If you have, okay. Okay, any other queries, guys? I'm sorry again, I have overshot my time. Yeah, some addresses like No, Abhishek, I am not going to teach you. वही बताया ना, I am इधर उधर निकल जाता हूँ. So I am teaching you assembly language, but it is not my job. I just taught you this so that you understand how a program works. Okay, and you understand, you can appreciate why you have a main memory. You can appreciate how a CPU works. Okay, I am not going to teach you assembly language programming. This is something that you will be taught in your computer organization course. Any other query?
Sir, can we store two instructions in the same main memory box?
No. For now, just assume no. Okay. You can actually, but for now, just assume no. You can only put one instruction.
Okay, sir.
So basically at this point, CU has essentially loaded. What usually happens is the computer always has some program to execute. So at the end of this program, the control unit resets the program counter to some other location in main memory, and that is the starting address of some other program. Okay, so congratulations, you are now a programmer. You understand how programming works. This is basically an assembly language program. You are not going to do this. You are going to work at a much higher level. But this is the overall concept. So all of you guys who are here, who are new, who are scared of programming, you understand how fun it is, right? I mean, you don't have to be scared. It's basically too fun. And usually we will not go at this level. It will be at much higher and much more comfortable level. But this is essentially what is a program. This is how you write a program, and this is how your computer executes it. Okay. And now this is the interesting part that some guys were asking, that we saw those load, add, store instructions. Okay. But in memory, they are not really different because a memory can only store zeros and ones. So even these instructions are also just sequences of zeros and ones. So for example, there's the load data at the rate 0110 instruction might have been stored something like this: 00011011, where the 00 is basically a code that basically means load operation. 0110 is an address, a 4-bit address of some memory location within the memory, and 11 represents the AC register. So essentially this means load content at 0110 to accumulator. Okay, so essentially you can see that this is also a set of bits, similar to that 1000 bit for 8, or any other bit. The only thing that is differing here, and now what I can also do is, for store, these 2 bits become 01 or 11. For add, it could become 11 or 10, whatever it is. For R1, it could be 01 or 10, something like this. Basically, what is the issue that you have to understand is, within the memory, they're all bits. It's just that if it is an instruction, the control unit has a predefined interpretation of how to interpret those bits. So it will interpret the first 2 bits as an operation code, the next 4 bit as an address, and the last 2 bits as some register. So any queries, guys?
So we can say that anything which gets stored in main memory is data, so that's why instructions are also a data.
Yeah, so essentially it is data, but you interpret it as an instruction. Okay, so something that whose address is in program counter, it is sure that it is an instruction. Okay, let's for now assume it like this, that the operating system makes sure that if there is an address in the program counter, whatever is stored, yeah, Aditya, I'll do that. So operating system makes sure that if there is an address stored in program counter, whatever is stored at that particular location, whatever person is sitting at that seat, is not really a data but an instruction. And but again, in the memory they are just zeros and ones,
Datas.
right? So how do you interpret it? What instruction is it? So you have to have some convention. This is a predefined convention which says the first 2 bit I'm going to interpret them as my operation code, the next 4 I'm going to interpret them as address, and the last 2 I'm going to interpret as an address, as a register. I can have any different, if the last 2 digits represent register. Guys, please unmute and ask.
Sir, if the last 2 digits are representing the register, then it must be like 00 for the first register and 01 is for the second, 10
Yeah.
for the third, and 11 for the fourth register. Then what
Yeah.
if there's a fifth register?
That is the point. So essentially, in this computer, you can only have 4 registers.
So if there is a fifth register, we have to change the main code to being able to store 3 numbers for the register code.
Yes.
Okay, sir.
Yeah. That how do, please ask, guys. And I am already late again. Sorry again. Um, uh, so please ask if sometimes I miss the chats.
Sir,
Yeah.
If this z double triple zero double zero double one can be a number also.
No, that is the point, that my operating system makes sure that if I'm reading if a particular location is stored, if a particular address is stored in program counter, it is an instruction and not a data, right? The confusion is right, that if you just have a look at memory, just have a look at the bits in memory, you cannot differentiate between data and instruction. But this is the responsibility of the operating system, to make sure that something that is executed is not data but instruction. Okay, so it points to a memory location. Program counter points to a memory location that is storing instruction and not data.
This means, sir, that it can differentiate between data and instructions.
Yeah, operating system can differentiate between data and instructions. Okay. Any other queries? Okay, sorry again, I have already overshot your time. Do you have a class? I think you will have.
No, sir.
Oh, very good. Okay, so probably they knew the kind of person I am. I'm going to take away your time, so they didn't schedule any class after mine. I just have like about 5-10 minutes of time more. So now there are 2 more things that you have to cover. So there is an input device. So how does this data and these programs get stored, right? The operating system is going to do that, but the operating system will ask it from you, right? You want to add 8 and 13. The operating system has no interest in adding 8 and 13. The operands, right? You maybe the addition program it already had, but at least the data items it will require from you. So there are some input devices in your system, where you basically input data to the computer. Okay, a typical input device is a keyboard. Now your operating system somehow understands how to deal with your input device. So when you press a key, what exactly happens? How does, let us say, 6 get converted into 0110? The whole protocol of this is understood to your operating system. We are not going to go into that detail. But what really happens is there are buses, there are wires from your input devices that run to your memory, and with the help of these wires, I can actually take up some data from the input device and store it in a particular address within the memory. Okay, so operating system is basically a collection of many assembly programs, and some of those programs also know how to operate your input device. It knows how to take data from your input device and then somehow store it at some location within the memory. And then there is in parallel the output device. So once your sum has been calculated, you have to give it back to the user, either display it on the screen or print it through a printer. The operating system knows that as well, right? How to deal, how to talk to your output devices. So you have a set of programs which can somehow talk to your output device and pick up something from memory. You always have. There was some question I did not see. So, but the idea is that your operating system picks up stuff from the memory and it has the capability of sending it to your output device. Again, you don't have to go into the details. You will study all this in your operating system course. So to summarize, this is the task that your operating system does. It manages your input devices, it manages your output devices, it manages the main memory, and it coordinates with your control unit to get the computation done. So basically, it just provides an easier interface to get your jobs done. Easier because in theory, we can directly communicate with the CPU. So now all those guys who are having a query, why do we have a memory? This is why we have a memory. We can store programs and operating system can then execute it on behalf of us. Okay, if without the memory, I'll have to simply talk to the CPU directly. And right, so you will study a lot about it in the operating systems course. Please ask any questions. I have one very small 5-minute presentation left for lecture 3 because I'm not available tomorrow. I'll just want to talk to you guys about it. If you have any questions, just ask. This is a very small presentation. So I'm starting with it, right? I already know I've overshoot the time. So basically, we understood that what this operating system is going to do, it is just going to make our life easier, right? Instead of talking directly to the hardware, the operating system is going to do it for us. Yeah, there is no class tomorrow, Tia. That is why I'm just figuring it, covering it today itself. It is just a 5-minute thing, and rest is homework. How do they transfer this? So basically, even though your operating system is going to manage these hardware devices for you, how they do that actually differs from one operating system to another. So they actually, so it is possible that the amount of stuff that you can do with your hardware depends on what your operating system allows or does not allow you to do. So for example, Linux is usually considered an operating system for programmers because it allows a much finer grain control to your hardware. Okay, whereas Windows and Macintosh, they are more closer to the user. They try to hide your hardware details, and then they try to be closer to you rather than to the hardware. Um, in some cases, I will. What is Linux? Okay, so this is another operating system. Okay, Linux is another operating system, just like you have Windows. You might be currently attending this presentation from a Windows laptop. So Linux is just a parallel for Windows. Okay? It is another operating system. And if you don't know what is Linux, then you have to go back and watch lecture 0 again. Okay. So basically, what if I do not have that my choice of operating system on my own laptop? So there are some software solutions which can help me. They are known as hypervisors. Okay? So hypervisors is basically a collection of programs which can emulate a hardware Okay, so this is something that is very difficult to understand right now because you have not read operating systems. But for the sake of understanding, just assume that what a hypervisor does is it emulates, it presents a kind of virtual uh, hardware, virtual CPU, virtual input-output devices, virtual main memory. Everything is virtual. Okay, so basically it's more like a hardware that is absolutely bare. Okay, now once you have an emulated hardware, you can try to install an OS, an operating system over it, right? Just like you installed the operating system on your hardware. So we call these kind of emulated hardware as a virtual machine. They are not machine. Machine is your laptop, but basically I'm going to create a virtual machine, an emulated machine on top of my machine, and they are known as virtual machines. So the overall idea is something like this. You have this hardware. On top of it, you might be already having an operating system, Windows maybe probably, right? Or Linux or whatever it is. So we call this operating system as the host operating system. This is the operating system that is directly running over the hardware. And then I install a software over it. Okay, this hypervisor is similar to any other software that you install on operating system. So how did you install Chrome, for example? You downloaded it from the internet, you ran the setup, and a program was installed, a software was installed on your laptop. So similar to that, you download a hypervisor, you run the setup, and it is just a program that gets installed on your operating system. Now what this hypervisor can do is it can now emulate. Okay, it can basically pretend that there is a new hardware which is sitting on top of my existing hardware on. Okay, and there can be multiple instances also. I can emulate not just one but two or three or more instances of hardware. And then once I have this emulated hardware, each of these emulated hardware have separate CPU, separate IO, separate main memory, right? And now you can actually install another operating system over the emulated hardware. Okay. So
Uh,
what? Yeah, go ahead.
Sir, will this emulated hardware makes our will it make our computer slow?
E- Um, so basically, this is just like another process. Okay, hypervisor is just another process. So it is similar to running Microsoft Word, for example. It's just that it is
But
it'll
it is still going to consume our memory and
Yes,
others.
yes, yes. I mean, it is going to be more in general. It is going to be a little more uh, expensive as compared to a typical software. But the best part is that you can actually control this emulation. So you can basically say, I only want my laptop has, let us say, 4 GB of RAM, but my emulated hardware only has 1 GB of RAM or 512 MB of RAM. Okay, I have two processors on my system, but my emulated hardware only has one processor. My RAM is my hard drive is 2 terabytes, but the emulated hardware only has 50 GB, something like this. So you can control it to a very fine grain.
So it will
Sir,
be used of
if,
what we had originally. Like we have 2 TB of a hard drive, and we give 50 out of that to new.
Yeah. So basically, you are of course limited by your physical resources. You cannot give more than what you already have. Actually, there are some restrictions that hypervisor will put. You know, but as I said, those are not really that important. I am not going to go into details of what emulation is.
Okay,
But
sir,
uh,
sir, if we
yeah,
start using guest operating system, then can we use host operating system
yes,
simultaneously?
yes. You can simultaneously use. Okay. The guest operating system runs pretty much like a process. It's a window.
Sir, sir,
Yeah.
sir, is a guest operating system can be compared to user interface?
Yes, it can. It can.
So will I be able to exchange files from the emulator and the main
Yes,
host
yes,
operating
yes, yes.
system?
Yes, you can. There are ways to do that. You can actually create shared folders between these two. You can copy their clipboard, right? So basically, you copy something here, Control C, and then you can go and do Control V in your guest operating system. So all this is managed by your hypervisor.
Okay, sir.
Sir,
Yeah.
sir, the cores of processor will also be divided in both the.
Yes.
Sir, example of VM, sir.
Pardon?
Example for VM, virtual machines.
So see, I actually did not want to do this, but let me just show you this. So this is let me just complete the presentation first. So um, I use a virtual Oracle VirtualBox. You can use VMware Workstation Player as well. These are two hypervisors which are common for personal use. You have to create a VM over it. This is your homework. This will also be a part of your first lab, so please do it. Now I'll just in 2 minutes I'll show you. This is a hypervisor. Okay, I have this VirtualBox, and I have two virtual machines here. One is with Windows, another one is with Ubuntu. If I start this VM, this is what happens. Can you see my screen?
Yes, sir, we can see.
Yes, sir.
Yes, sir.
Okay, so then I'm starting a virtual machine on my VM on my laptop. So you can see this is my this is my host operating system. It is Macintosh, and in the background, in the virtual machine, I have started a Ubuntu virtual machine, and this is what happens. This is my Ubuntu. Okay, so this is just my Ubuntu virtual machine. I was doing something, so it is already here. So this is Ubuntu. You can see. Okay, on as a process. So for me, this is just a window. I can minimize it like this. Is it clear now? So this is just an idea of what a VM is. And I'll just save it. So basically, you have to do this as part of your first lab as well. And please, I'm really sorry I could not cover this in detail because I cannot take tomorrow's lecture. I have the exam scheduled in the same slot. So it is not too hard. You just download it like a simple program, virtual box download. Next week, not this week. They just next week. Okay. So you can just go to VirtualBox and you can simply download similar to how you download any other software. So you can do it for Windows, for Linux, for OS X. You'll get a setup. You just run the setup and install it. Okay, it is as simple as that. So please do it. Read a little bit more about VM. I'm really sorry I had to abandon you like this. But yeah, Abhishek. These ISOs are I'm really sorry. You can actually pick up some other some other flavors. So you also have the server versions of Ubuntu, which will not be as big as this 2.59. It should probably be in the 800 to 900 MB range, the server version of Ubuntu. So to start with, you can actually just install the server version, and maybe later you can, if you require. We won't really require. I don't think I have anything planned for which you require UI. At least not in the first phase of your course. So for now, just download a server version of Ubuntu ISO, and that will be much smaller in size. So any other things, guys? Again, I'm sorry I have taken so much time.
Sir,
Yeah, go ahead.
sir, can't we directly partition the hard disks of a system?
It's up to you. It's up to you. The reason I suggest using VirtualBox is because of the snapshotting. Just go and read the the homework in the slides. The slides are shared at the same location in the Google Drive folder. So you have to do the homework. You have to read about what is snapshotting. I just okay. Let me give you 2 minutes more. The other batch will say, sir, you didn't show us to us. That is why. Um, so this is this is basically a snapshot. Okay. I can actually create so snapshotting basically means I just take a picture of my virtual machine at any point of time, and then I can keep it stored, and then even if I mess up something, I can go back and restore my machine to some of this point. It is similar to system restore in Windows, if you have used it sometime, right? It is much better than system restore. System restore will only restore your programs, okay, and some settings, not the files. This will basically restore uh, your whole virtual machine, everything from data to programs, everything. So this is why I said, it is better to use a VM. It is up to you. Any other queries, guys? Ankit, do you have a query?
So after we install VM set, then we have to install some OS as well.
Yes. You have to install some OS. And I strongly suggest some Linux flavor. Okay. In the lab, you will have to install Linux. So please be prepared. Okay. Try to yeah, Kali Linux is okay. Any Linux is okay. I'm not no, I have no issues with any particular Linux version. Just use whatever version of Linux you are comfortable with. It's just that if you are first time entrants in the world of Linux, then I particularly would suggest Ubuntu. But as I said, don't take me in as the expert on this. Yeah, fine. Anything, Himanshu. Some version of Linux. You should have a terminal. That's it. All I need for you is you should have some terminal. As long as you have a terminal, I don't care what operating system it is. So yeah, guys. Anything else? Again, very sorry. I have already overshot the time. Since once we exit, we does the hardware division. The hardware division. So the hardware never gets divided. I mean, it's just emulation. It's a process runs, and it shows your guest operating system as if it is operating on a hardware. That's it. As soon as the resources that your VM uses, they are released when when you shut down the VM. You don't, so basically only when you run the VM is your resources, your resources are only used when the VM runs. Otherwise the resources are free. Yeah, like BlueStacks. Okay. Any other queries, guys? Again, sorry, no, I had to.
Sir,
Go
do
ahead.
we have labs tomorrow?
No lab, no lectures this week. Okay, week 0 is done. And week 0 was basically this was foundation week. Foundation week is over. My job was to try to bring all of you to this everything, right, Adit? Everything, the videos, the slides, everything is there it will be there in the Google Drive folder. I have shared it with you guys. 4 GB. Yeah, Vanshdeep, what you can try is you can try to create a VM with just 1 GB of RAM and use some server version of Linux, like Ubuntu server. Okay, they are much lighter in weight. So use a server VM and server. Prathamesh, it is there, right? I mean, guys, can you please help Prathamesh? Some of you have already figured out where is that folder. So please somehow, coordinate with each other. And I just want everyone to have access to that folder. Okay. So talk to your friends. They know how to access that folder. It is already shared with you.
Okay,
Yeah, you
sir.
can have dual boots. Yeah, you can. Yeah, you can have dual boot. Okay. Do no. The overall idea is that you should work on Linux. I can't force you. This is not my job to force you to use Linux, but this is my strong recommendation. The rest is up to you. But Alpesh, that is really I mean, I will cover some very basics of Linux, but I'm not sure I can cover a lot. You will have to basically learn it on your own. I'll give you a brief overview of Linux. Then week one is all Linux actually. Week one is all about Linux. Whatever I can teach you in week one, I will teach. But most, it's um, um, so if you are running Rohan, if you are running some UI based version, like Ubuntu. So by the way, I use L Ubuntu, not Ubuntu. L Ubuntu is a lighter version of Ubuntu. So if you want to use Ubuntu, just download L Ubuntu. L Ubuntu will require much less amount of RAM. So I have only allocated 2 GB of RAM to L Ubuntu. 2 GB is more than enough. Um, but it can probably work in 1.5 GB as well. Um, but if you are short on resources, you can always download a server version of the operating system. Just read what is the difference between server and desktop versions of operating systems, and you can download the server version. They are usually much lighter. They'll be they'll be only 800 900 MB. The ISO will be smaller. They will take lesser resources, but basically server versions are just command line versions. There is no UI. Okay, any other queries, guys? I'm sorry again for taking up so much time. That you can download anyhow, Nishant. I mean, you can just type Ubuntu ISO, L Ubuntu ISO, Kali ISO. Just type this on Google and you will get the ISO. Any other queries, guys? Okay. Thank you, guys. And from next week onwards, we are going to work in that shepherding mode. So, practice your your communication skills, group directions, group discussion skills. We will have there are no labs this week. There are no more lectures this week. I'm always there on email. So you can always ask your queries over email. Some of you have already done that. You can continue to do that over the next few days. Okay. Thank you, guys. Bye, everyone.
मैं नहीं जा रही क्या?